Good day, everyone, and once again we are back together, and this time we're going to be looking once again at the fundamental counting principle. So if you haven't subscribed, please just make sure that you hit that subscribe button and be part of the family. And of course, you can get in touch with us. All our details are on the description of the video. Of course, you can visit our website as well. That's www.mlungisinkosi.co.za, and get in touch with us on our email as well. All right, so we've started part 1 on the fundamental counting principle. Okay, so this time we're going to be starting with part 2. And of course, there's also a sequel to this video. So I hope that you enjoy the lesson. Please, at the end of the lesson, don't forget to like and share. And, just tell as many people as you possibly can, about the value that this channel is bringing. All right, as you prepare, let's get into the lesson. All right, now let's begin. So when we started, we spoke about the fundamental counting principle. And we said, look, if we have an event that can be done in M ways, and a second event can be done in N ways, and a third one can be done in K ways, then we know that the total number of possible outcomes in this case would be the product. This is what we call the product rule, right? We spoke about that extensively in our first video. If you haven't watched that, please just go back and have a look at that, right? But in this case, I won't even talk about an example on that, but I wanted to now, or maybe let me just explain something about this first one. Remember, this is, in this case, for independent events, all right? So it means that these are events that are not dependent on each other, and in this case, they're not occurring simultaneously, right? So we said the total number of outcomes would be the product. Now, we also have what we call the sum rule. I may not have alluded to this in the first video. Now, in the sum rule, what it simply says is that if we've got 3 events, it can be 2, it can be 4, whatever the number of events. I've just taken 3 as an example here. If it can be done in M ways, and another one in N ways, and another one in K ways, then the number of choices to do one of those events, okay? One of those 3 events is M plus N plus K. Now, I'm going to make an example on that, okay? So now, the sum rule would actually be applicable when we have choices that are not independent, okay? Right. So in this case, it means that the choice that you need to make is dependent on some other function or the other, right? Now, let's make an example on that. Now, let's take, for instance, where we've got 3 models of cars that are found at a dealership, né? All right, so we've got a Toyota, a Mazda, and a BMW. And you can choose any color, right, between black, white, blue, or red. You can even choose the type of interior that you want. Between black interior, white interior, and caramel. All right. Now, if they tell us that black BMW, that is in this case the color of the car, is out of stock, right? Now, determine the number of available options to choose from. Now, do you agree with me that in this case, the option of the car, or rather, the car that you choose, would determine the number of options that are available, right? Meaning that the number of outcomes now is dependent on the type of car that you choose. Why? Because remember, BMW is out of stock. So not all BMWs have all the variants of the colors that we want, right? Now, how are we going to get the outcome? Of course, in this case, if all the colors were available, if all of the makes were available, in this case, all we could simply do was to say, look, it would mean that the total number of outcomes would simply be, how many cars do we have? We've got 3 cars. We've got 4, in this case, options in terms of color, but also we've got 3 options as well in terms of the interior, right? But we can't do that in this case, right? Why? Because remember, BMW in black is out of stock, right? Now, what would be the total number of outcomes? So in this case, the outcomes that we would have would be equal to, now note, let's first talk about the other two brands where we are not limited in terms of, the color. So in this case, I've got Toyota and Mazda. So how many options do I have? I've got 2 options, right? And in this case, they've got all the variants in terms of color. So that's multiplied by 4. So they've got also all the variants in terms of interior. So that would be multiplied by 3, right? Plus, now notice, or, so immediately when I say or in this case, I would add a plus, and that's where the sum rule comes in, right? So in this case, or I could choose a BMW, so that's 1 car, right? In this case, the BMW does not have black as a color, so it has only 3 options that are available. So that would be 1 multiplied by 3, multiplied by, well, the interior has all the colors available, so that's multiplied by 3. All right, so of course you can find the answer to that. That would be 2 times 4 times 3 in this case. Remember, 2 times 4, that's going to be 8. 8 times 3 is going to be 24. Okay, and then 1 times 3 times 3, that would be 9. So that would be 24 plus 9, and that would be 33. So it means that the options that you would have available in that case would be 33 options. I hope that you understand the rule of sums. All right, now let's talk about arrangement of objects, right? So in the first instance, I'm going to refer or rather talk about where repetition is not allowed or is allowed. And obviously in the second instance where repetition is not allowed, and we're going to just unfold and talk about committees and forming passwords and mixtures of words and so on, right? Now, in this case, if we've got an arrangement of object, we say, well, if R of n objects, these statements, I know they kind of never make sense, but you'll understand in just a few. Right, so if R of n different objects can be arranged, or rather R of n objects can be arranged in n to the power R different ways if repetition is allowed. Now, what do we mean by if repetition is allowed? It means if you can use the same object, many times, right? Now, I want us to take an example in this case, right? So they say, determine using 5 color crayons how many arrangements of 6 crayons in a row is possible if repetition of colors is allowed. Now, let's say you've got many crayons, right? And in this case, the colors that you have are blue, red, green, yellow, and black, right? So you've got 5 different colors, but you've got lots and lots of crayons. Now, what you want to do is you want to make different sets, okay? So suppose that you've got, you want to make 6 sets, right? That's what they said. They said how many 5 color crayons, or rather how many arrangements of 6 crayons, right, can be made. So in this case, that's 1, 2, 3, 4, 5, and 6, right? So in each of these boxes, you're going to put a different crayon. But remember, you can use the same color many times, isn't it? So you can, for instance, put all red in all the your color combinations, or you can put all blue, or you can put, you can use, the same color many times, right? So repetition is allowed. So now, think about it. So in the first instance, how many crayons do you have, or how many options of crayons do you have to choose from? You've got 5 crayons, isn't it? So in this case, you can choose from the 5, right? In the second one, how many colors can you choose from? You can choose from 5, right? Remember, in this case, the fact that you've used one color does not prohibit you from using that color in the next in your next choice. So in this case, you are allowed to use the same color, right? So how many choices do you have in the third one? Of course, you still have another 5. How many choices do you have in the next one? You've got 5. You've got 5 and you've got 5. I hope that makes sense, right? So as I said, you can use the same color many times. So in this case, what would be the total number of outcomes that you can find? So in this case, that would be 5 times 5 times 5 times 5 multiplied by 5. So you can actually put this as 5 to the power of 6. So do you remember what we're talking about there? Right, in our statement, that if you've got r of n different objects, right, that can be arranged, they can be arranged in n to the power r. So in this case, we're looking for 6 combinations, right, in this case of colors, but out of 5, right? So in this case, our choice would be 5 to the power 6. And if we take that, let's say 5 yx6, we get an answer of 15,625. That's the number of possible outcomes that we can create if repetition is allowed. All right, now let's consider a case where duplication is not allowed. Okay, so we'll talk about, or we'll compare the two. Right, now we say arrangements of objects, right? So if we've got n objects with identical objects r, p, and k, can be arranged in, well, n factorial, so that means the total number, divided by the number of times that you've got repetition. Okay, so this also works when you've got words, for instance. Okay, we'll talk about that a little bit later. Right, so it means in this case you would have that number of different ways in which you can represent that. Now let's take an example. Suppose I've given you there 12 crayons, right? So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, right? And in this case, you've got 12 crayons. However, you notice that in this case, you've got crayons that have a similar color, right? Now, they want us to find out in this case how many different ways in which we can arrange these crayons, right? Now, let's consider the first possibility, right? Let's say if duplicates are allowed. So in this case, it means that even if you've got different colors, but you sort of take them as though they were different, right? So what are we going to do in this case? So if duplication or if repetition is allowed in this case, what can we possibly do? Well, how many combinations or how many ways can we possibly arrange? How many arrangements can we have? Well, in this case, all we simply say is, well, we know we've got 12, so that would simply be what? 12 factorial. Okay, 12 factorial ways. Now, let's see. If you took 12 factorial, okay, so that's shift. There we go. Oh, that's a very huge number. So that would be what? 479 million? Yeah. Okay. 1,600. Okay. Right. So 479 million. 1,600. So that would be the number of arrangements that you can make, right? But now, if they say to us that repetition is not allowed, it means in this case, you now have to factor in the factority that there are different colors of crayons. Okay, right. Now, in this case, what are we going to do? Right, let's look at the colors that are similar. Well, can you see I've got black and black there? Okay, so I've got two blacks. So let me, so I've got two black. Okay, and then let's see another color that is, so green. Okay, we've got only one green. I've got two reds again. So I'm going to note that I've got 2 red. Okay, right? So again, which other one? I've got 3 blues in this case. So I've got 3 blues. Okay, so in this case they are repeating. And I've got 2 yellows. All right, so I've got 2 yellows in this case. 2 yellows. All right, and it seems like there's no other color that is repeating in that case. Now, how would I find the number of different arrangements? And this is where a formula comes in, right? Now, how many repetitions do I have? I've got 4 of them, right? So it would be n factorial, remember, divided by the number of repetitions. So in this case, I'm just simply going to say the number of black factorial multiplied by the number of red factorial multiplied by the number of blue, let's call it blue prime, b prime, right? Blue factorial multiplied by the number of yellow, okay? In this case, factorial. All right, so that would be the number of possible outcomes that you could have. So you would say, well, in this case, you've got 12 factorial divided by 2 factorial multiplied by another 2 factorial for the red, multiplied by another 3 factorial for the blue, okay, multiplied by 2 factorial. All right, so you can do that for yourself. We already have 12 factorial, so I'm just going to divide that by, so I'm going to say 2 factorial multiplied by another 2 factorial, okay, multiplied by 3 factorial multiplied by another 2 factorial. Okay, right, and the number of possible outcomes in this case, or combinations that I would have, that's 9,979,200. So it means that's the number of possible outcomes that I have if we say that we are factoring in repetition. Okay, right, I hope that makes sense. So if we take, for instance, the word mathematics, right? So we take it as though each letter is different. So mathematics, right? How many different ways in which the letters could be arranged if repetition in this case was allowed, right? So it means that we're going to take each word as though it is a unique, or each letter rather, as though it was unique, right? So in this case, we're saying, well, if repetition was allowed, how many letters do we have? We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11, right? So simply put, we would say, well, 11 factorial. What is 11 factorial? Well, what do we get? Yeah, that's that big number. So that's what? 39 million? Okay, 916,800. Okay, so that would be the number of outcomes, or in this case combinations that you would create, or the number of arrangements that you would create if repetition was allowed. But now, if they tell us that repetition is not allowed, so meaning that we are now factoring in the words that are repeated, or rather the letters that are repeated, right? So I see M is repeated 2 times, so I've got M that's repeated 2 times. I've got A in this case that's also repeated 2 times, so I've got A that's repeated 2 times. I've got the letter T that's also repeated 2 times. Okay, so I've got T that is repeated 2 times. Okay, H is on its own. Okay, and yeah, every other word is sort of on its own. So in this case, what would be the number of possible outcomes? Well, we would simply say in this case that's 11 factorial divided by 2 factorial, that's for m, multiplied by 2 factorial, that's for a, multiplied by 2 factorial, and that's for t, right? So in that case, you would simply calculate that. So I'm just going to say divided by 2. Well, 2 factorial is 2. 2 times 2 times 2 in this case. And that would give us 4,989,600. All right, so ladies and gents, I hope that kind of makes sense to you. Right, and please remember that you can always visit our website. That's www.mlungisinkosi.co.za. You can see the tabs at the top there. You can get past exam question papers from this website. Okay, all your matric past papers. Of course, we're still going to load some more as well. Also IEB papers as well. You can also just check out courses in this case. So if you want to get a more structured approach to our course lessons, they are all free, right? So say for instance you wanted to go to acids and bases, you just click on that and it will show you all the videos that are on acids and bases, and you can actually watch them sequentially. All right. Yeah. All right, just one last thing. Of course, you can always visit our channel, just to see the most updated lessons. Please always make sure that you are subscribed to the channel. We're trying to get to that 100,000 mark. And thank you for those of you who've been part of the journey. And now we are at over 80,000. Of course, you can always check out our most updated videos, okay, to go and check what our lessons look like. And you can use the playlist feature to try and see the lessons in how we've ordered them sequentially. We've tried to group them into playlists, so you can use that particular feature. And finally, ladies and gents, you can also use the super thanks feature. All right, so if you want to look at it there, you've got your super thanks. You can actually give a monetary gift, just to say thank you to your favorite uncle for the lessons. All right, and I just want to keep it there for today, right? All right, ladies and gents, I hope that you enjoyed the lesson and that you were able to follow on what we're doing. Of course, you are welcome to get in touch with us. Otherwise, from me for now, I'll see you guys again next time. Sharp, sharp.